Hello teachers, let's continue our conversation of section 13-4 where we're talking about surface area, and it's going to be the surface area of different figures. In part 1 of the video we talked about surface area of prisms and pyramids, and you'll see in front of you right now you have the figure of a pyramid with a regular square base here, and then we moved on up to a how many sides does this thing have? 1, 2, 3, 4, 5, 6, 7, 8. A regular octagonal base, and then we moved up. Maybe there's 16 sides there, who knows, because I don't want to count them. But the idea is this: if we increase the number of sides, and notice the sides get smaller and smaller, if we increase the number of sides, that's going to approach a circle. And that was originally how the area and the circumference, especially the area of a circle, was calculated way back in the day, is to approximate, take a polygon and approximate it to a circle by increasing the number of sides. Now, all that to say that we're going to discuss the area of a cone. Okay, so the surface area of a cone is pi r squared plus pi r L, where r is the radius of the cone and L is the slant height. Notice my L's are a little different than the picture. Should have made those more script, but that is the same L. So again, keep in mind when you see slant height, especially when you see that L, it is not the altitude, okay? It is the slant height out here, whereas the altitude is the dashed line that goes to the center, which would really be the height of the cone. All right, so again, pi r squared, what is that part? You recognize that, right? That's the area of our base. So this pi r squared part of the story down here is just the area of the base. So this is the base. And then pi r L is the area of the surface. So this is the lateral surface, if you want to say that. Does not include the base. Now, one way to think about that formula, if we, remember in the last video, I asked you to picture taking that pyramid and just making all the sides just fall out flat. Well, that's what we could do here if you could sort of picture that. But again, you have to picture this is not a circle when you do that. And you have to picture that this is a polygon with a whole bunch of sides, right? Okay, so if we have a polygon with a whole bunch of sides, then B down here is like your base width of your triangle. Now remember, when we added all that together, that was pi r L, where r is the radius, okay, of the circle, right? Not down here, but the radius of the circle times the L is the slant height going on. And that corresponds to H, which is like the height of that piece of the triangle. So it's still kind of a jump to go from this idea to that being pi r L. But you can imagine adding all of these areas together, okay? And we know the area of a circle is 2 pi r. But we have the triangle, there's 1/2. Maybe that's what happened to the 2 pi part, the 1/2 of the 2 pi, and the perimeter is 2 pi r. Do you see what I'm saying? So if you added the perimeter of all this, which is a polygon, but that approaches the circumference of a circle, and again, we had those 1/2s because of all the triangles. So again, it's a jump. It's not a full explanation, but maybe it's enough to make you go, okay, I'll buy into it. So let's actually use it for a calculation. That's what I really need you to know. Okay, so find the surface area of the cone, right? Do we need to go back and grab the formula? To remember, it was surface area. I'm just going to write SA. And again, this is of a cone, not any surface area, but of a cone, is pi r squared plus pi r L, where L is the slant height. Okay, do we have all that information to start with? So do we have the radius of the circle? We do, right down here. That's our 3 centimeters. Okay, do we have our L value? We do. Okay, that's the 5 centimeters. Now, do we need anything else to pull this off? You know, it's just got the R and the L and that's it. So do I need the 4 centimeters for anything? Now, what is the 4 centimeters? That is the altitude, or how tall this cone is, and you don't need that. You would need it if you didn't have the 5 over here, though. Watch out for that in the homework. So often you have the altitude and you have the radius, but you don't have the slant height. I cannot get that word out. It's the slant height. Okay, so anyway, here we go. So surface area is equal to pi and then r squared, so that's going to be 3 centimeters squared, plus pi times r is 3 centimeters times L is 5 centimeters. All right, so I keep going. I'm going to scoot over for space purposes. This is pi. 3 squared is 9. Centimeter squared is centimeter squared. Plus pi. 3 centimeters times 5 centimeters is 15 centimeters squared. Again, centimeter squared and centimeter squared means I can add these together if they both have pi. If they don't both have pi in each term, I cannot add them together, but we do here. Let's write it in a different order. How about 9 pi plus 15 pi, and then leave the centimeter squared out back? There we go. And then we know 9 plus 15 is 24 pi. Now again, real quick, maybe obvious to some, but not to all, I cannot add these two guys together unless they both have pi in them. And in this case, they do. So you'll have other types of problems that have pi in one term, but not in the other. And in that case, you cannot add those terms together. But 9 pi plus 15 pi really is 24 pi, and you keep the centimeter squared. Now, you want to check their version of this? Sure, they're going to make short work of it. There it is, 24 pi centimeters squared. All right, how about the surface area of a sphere? It's actually a pretty easy formula. We're not going to derive it whatsoever. I'm just going to tell you what it is. Okay, now, they call this the great circle. Why do you think they call that the great circle? Well, because it goes through the center. Okay, so the center of a sphere, because there are tons of circles in here. If you took this sphere, or just picture taking a solid ball, like one of those Nerf balls, and you start just slicing it into segments, okay, parallel segments, they're all going to be circles, are they not? So the great one, that's the biggest one, is going to go through the center. All right, now the sphere surface area is 4 times pi r squared. Okay, you got that? Now when we get to volume, the volume of a sphere is different. So again, surface area is 4 times pi r squared. Now I don't even have an example ready for you to go here, so let's make one up real fast just to say we did it, right? So let's say the radius of the great circle, which is really the radius of the sphere. By the way, let me ask you this before we do this problem. How many great circles are there for one sphere? And I know you might be thinking there's just one, right? That one right there in the picture. Y'all, there's an infinite number of them, because I didn't have to cut it this way. I could have cut it this way, vertically. Or I could have cut a slant to it. Now I got the word slant, right? I could cut this anyway. There's an infinite number of great circles. I could move it around. But what we know is that the area of a sphere is 4 times the great circle. Again, we're not going to derive it. It's a calculus situation, so you probably don't want to see the derivation of that right now. Although if you're interested and you've done some integration before, you can certainly derive the area of a sphere, but we're not going to touch that, and we're just going to use the formula. What if I said that we had a Nerf ball, and that it had a radius? How big is a Nerf ball? My daughter has one that's about 6 inches. Okay, we want to know the surface area. So it would just be 4 pi times 6 inches squared. This is exactly why I don't have example built in. You have to do your square first. Remember, order of operations. Parentheses first, so then exponents. And this is not what I mean by parentheses. I mean I put them there to say the 6 inches squared, but really we're doing exponents at this point. So it's 4 times pi times 36. That does change that to inches squared because I squared it. And then we multiply 4 times 36 and just leave the pi in the answer, might as well, unless we needed a decimal approximation. And that would go at the top of the page because I can't fit it here. That'd be 144 pi inches squared. Do you really want to know how big that is? Just multiply it times pi. And that would be 452, if I round to the nearest whole number, 452 inches squared. That's a lot of surface area for just a 6-inch ball, don't you think? Now, as typical, I've got a couple of homework problems that I want to help you out with, just in case you get stuck. These are great problems, I think, but I just don't want you to feel stuck, so I like to do them in the videos. So the napkin ring pictured in the following figure is to be resilvered. How many square millimeters must be covered? Whew. Okay, so we got a napkin ring over here. I'm going to use my color because you know I like to. All right, so let's break this down into pieces and parts, right? First of all, that is a surface. That is a ring. Think about how we're going to calculate that. All right? That surface also appears in the bottom. So we're going to have 2 of those surfaces. Just picture it as just a flat. This is surface area we're doing, right? So there's 2 rings, the piece at the top, the piece at the bottom. Then you have the outside part of your surface area, like the can of soup on the outside, but you also have the inside part because it needs to be silvered as well. So let's think about all of our parts here. So we have the inside surface area. I'll leave some space for calculation. We have the outside surface area. And then we have the 2 rings. I'm just going to call it the 2 rings, which I have highlighted over there in green. All right, here's the next problem. How many square millimeters? I don't know if you noticed this right off the bat, but you would have when you started your calculation. I'm positive that some of the units are given in centimeters. I'm about to lose part of this over here because my screen is not showing enough. So some of this is in centimeters and some of this is in millimeters. Whew, maybe we should put all this in millimeters. And it does ask, look, how many square millimeters must be covered. So that's your sure sign to put all of this in millimeters. So 3 centimeters we know is 30 millimeters. And 2 centimeters out here, which is the height, by the way, is 20 millimeters. So the height, I'm going to put it over here, the height is 20 millimeters. And then the radius inside is 30 millimeters, and this thickness, the wall, is 2 millimeters. Okay, so the surface area on the inside. Now, we know this is a cylinder, right? Now, do we need the base? Because there is no base. A napkin goes in the middle of there, so there is no base. We're just doing lateral surface area. Do you remember the formula for a cylinder? Remember, a cylinder really is just a rectangle. Right? So it's just the base times the height. Like if you unfolded this soup can right here, it would give you a rectangle. And it's 2 pi r times h. Okay? I should have put that at the top. Let me do that. 2 pi r times h. That's a formula for just the lateral surface area. And we're doing the inside. Okay, well the inside is 30 millimeters. So it's going to be 2 pi, and that's 30 millimeters, times the height, which is 20 millimeters. You cool with that? All right, how about the outside? Same formula, different stuff we got to plug in though. So it's 2 pi. Okay, now the radius, the r value, well, it's 30 millimeters plus 2 more millimeters because of the thickness. So the outside is 32 millimeters times the height is still 20 millimeters. All right, now how about our 2 rings? How are we going to calculate that? First of all, we're going to put a big 2 in the front. Let's don't forget there's 2 of them. But this is the area of a circle, right? it's really the area of two circles, because the only way to get a ring is to take the outside circle and minus the inside circle. So again, I'm going to do 2 times the outside minus the inside area. This is the area of a circle. Okay, what's the area of a circle? You know it well, right? I'm going to write it down here below. That's pi r squared. So this is going to be on the outside part. It's going to be pi, and the outside radius, remember, was 32 millimeters. And we're going to square that. Minus the inside is going to be pi r squared is 30 millimeters, and then squared. Now we just need to run all these numbers, okay? And what are we going to do with them? We're going to add them together, because it's going to be just plus, 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 and then our final answer at the bottom. Now I'm going to erase our pi r squared down here. We've used it up. We don't need it anymore. And run some numbers. So stand by. I'm going to play with my calculator, write them all down, and come back with them written down. All right, so the inside I wrote first at the bottom here. So 2 times 30 times 20 gives you 1,200, and I just carry the pi along. Okay, that is millimeters squared, by the way. I'm saving that for the end. And then 32 times 20 times 2 is 1,280. Make sure that seems reasonable. This one is more than this one and should be, because the outside's bigger than the inside, right? And then I went ahead and calculated this. So 32 squared minus 30 squared gives you 124 pi times the 2 rings. So that's 248 pi. Now I'm going to add all those together. So 1,200 added to 1,280 added to another 248, and that's 2,000, let's do it, 728 pi, and that is millimeters squared. That's a fun problem. I know you could have done that by yourself. I know you could, but I thought it would make a fantastic lecture example as well. Okay, let's sneak in, is it 1 more or 2 more? I have 2 more actually. So here's another one. So the base of a right pyramid is a regular hexagon with sides of length 6 meters. Okay, now I am not so fantastic at drawing anygons. Triangles I'm not bad at. Squares I can pull off. Rectangles are not so bad. Okay, hexagon has 6 sides. That's what's important. And it's supposed to be regular, which is where the problem comes in. But there you go. There you go. Now, I'm not going to turn that into a pyramid, okay? But that is the base of our pyramid. It says with side lengths of 6 meters. So every one of those guys is 6 meters. It says the altitude of the pyramid. Now, picture a pyramid coming out of here. So all I'm going to do is this right here. Okay, this is the altitude. Okay. So there's your pyramid coming out of this hexagon. The altitude is 6 meters. So that guy right there is 6 meters. All right. Oh, no, 3 meters. I am not reading because it's teeny tiny. So let me try that again. 3 meters. There we go. Find the total surface area of the pyramid. Okay. Now, do you remember how we need to do this? You need to go find the pyramid formula for surface area. Let's go do it. So I'll scroll back for you. I think this is even a previous part of the video. But it says the surface area is 1/2 PL plus B. Let's write that down, and then we'll talk about it. 1/2 PL plus B. So surface area is 1/2 PL plus B. What is all that stuff? Okay, so P, remember, represents perimeter. L represents the slant height. Ooh, that's the slant height. They didn't give us that, by the way. Plus B represents your base. So we're going to have to find the base of this pyramid right here. The area of the base. So we need to know the area of this thing. All right. Now, I don't know what part you want to tackle first. And you might be saying, I don't care. You just tackle it, right? Well, let's go ahead and work with this area over here. So way back, we talked about the area of an n-gon. We have a formula for that. So the area, I'm going to write this down, the area of an n-gon is 1/2 AP. What is AP? Well, we've already established P is a perimeter, right? Okay. Now, remember, you're talking about just two-dimensional space here. So we're talking about A is like the altitude of your triangle. So this, oh, come on now. My pen was working just fine. Okay, so this is the altitude of our triangle. So how do you suggest that we do that? Let's label everything we have, right? So it said the base of the right pyramid is a regular hexagon with sides 6 meters. So again, 6 meters. This is 6 meters. Okay, now that altitude came down and cut this guy in half. That's a 3 right there, right? Now, tell me about these triangles that are inside a hexagon. Anything significant about triangles inside a hexagon? There's 6 of them, right? And how about each of those are 60 degrees? So that would be a equilateral triangle. So this is going to be 6, and then this is 6 and 6. So recognize this triangle. This is a 30, 60, 90 triangle. You could either use the Pythagorean theorem and say side squared plus side squared is equal to 6 squared. Let's do that. Okay, so 3 squared plus, we're looking for the A squared as altitude equals 6 squared. Okay, so that's going to be 9 plus A squared is equal to 36. Subtract the 36 over and you get A squared is equal to 27, which means A is equal to, I let myself in a frame, the square root of 27, which breaks down into 3 square root of 3. And so that's our relationship too, that the shorter side, or the shorter leg and the longer leg is the shorter leg times the square root of 3. So let me do this in green. This guy right here, this altitude is 3 square root of 3. So when we find the area of that base right here, okay, it's 1/2 AP. So that's 1/2. A is 3 square root of 3. And the perimeter, we have 6 sides, 1, 2, 3, 4, 5, 6, that are 6 meters long. So that's going to be times 18. So we've got the B handled. We'll simplify that in a little bit, but we've got that handled, okay? Now what about now we're dealing with the height of our pyramid. Remember, it said that it had an altitude of 3. That's that value that comes straight down. What is this value right here? That's 3, right? Do we decide that's 3? That's what comes out? No, it's this value right here that's coming from the center. That's what we just found. That is 3 square root of 3 right there, y'all. So this is coming from the center now of your base, coming out here, and then the triangle builds up to the top. So this is that slant height. Now how am I going to find that slant height? Pythagorean theorem again, here we go. So I've got side squared, so 3 square root of 3 squared, plus side squared, which is 3 meters, which was the height of the pyramid, is equal to the slant height. I'm going to call that L squared. Now 3 square root of 3, remember when you have a product raised to a power, you square each. So 3 squared is 9. The square root of 3 squared is just 3. Plus 3 squared is 9. That equals to L squared. All right, 27 plus 9 is 36 is equal to L squared. So what does that mean L is? That is 6. I wrote 36, I meant 6. I'm going to have to go back and look at this one and break it down a little bit slower. I feel like I'm all over the place here. I apologize. So when I plug into this part, and I'm going to change colors to purple so you can see that this is 1/2. P, again, is the perimeter. Okay, all the way around, that was 18. Times L, which is 3 square root of 3. No, it's not. It's 6. My word. I think I'm getting tired. I apologize profusely. Okay, 6. Right, it's right there. There's my L. Okay. Now I'm ready to calculate. Okay, so here we go. I'm calculating this guy, and I'm adding it to this guy. So half of 18 is 9. 9 times 6 is 54. So this is 54 plus, over here, I have half of 18 is 9 times 3 is 27 square root of 3. That should be my final answer. Notice I cannot add these two together because this one doesn't have a square root of 3 and this one does. Just like if one of your terms has pi and the other one doesn't, those are not like terms. You can't add them together. So this is our final result here. Maybe the next one won't be so all over the place. And oh my gosh, I really should start this video over. Not the whole video, just this part of the video. But listen, I found an error. And it's actually the simplest. It's not the complicated stuff. Our p-value, remember we used it in 2 places. Let me highlight it for you. I hope you caught it. I bet you were on it. Probably like, I thought I knew what I was doing and I didn't. The p-value, that's the perimeter of the base, right? I put 18 2 different times, and I'm not really sure why I did that. But listen, it's 6 plus 6 plus 6 plus 6 plus 6 plus 6, right? That's 6 times 6. And I think there's so many 3's floating on this page that I guess I did 6 times 3, but I did it twice. 6 times 6 is 36. So it doesn't change much. Just hang with me. This is 36, okay? And this is 36. So let me go back and fix this. I'm so glad I noticed it then, where I don't have to go back and edit the video or anything like that. So we are at 1/2 times 36 times 6. I'm going to be really careful here. So 1/2 times 36 is 18, and maybe that's what I was thinking. I don't know what I was thinking. But 18 times 6, I'm going to use my calculator and not my head because I think my head's off a little bit. 108. Ooh, I feel better about that. Plus, okay, let's try this again. Now, 1/2 of 36 is 18. I still have to multiply 18 times 3 square root of 3. So 18 times 3 is 54. And then that square root of 3 just tacks along. Okay? And I just stopped it before I moved on to the next problem, and I was checking my work, and I'm like, oh my goodness. There's so many tiny little details to this problem. It's exactly why I wanted to show it to you, so you could see all the tiny details, but they're easy to get confused. Okay? And so, again, just a silly mistake, but a silly mistake to make you think you don't know how to do the problem when probably you were following along just fine. Again, we had to use the Pythagorean theorem twice. We had to find the altitude of the base. We weren't given that, and that was just to find the area of the base of our hexagon. And then we had to find the slant height. Sometimes you're given the slant height, and I said feel blessed when you are, because sometimes you're not, and you're going to have to use the Pythagorean theorem to pull that off. And I couldn't even do that until I found this value first. I had to use that value twice. Okay? All right, so hopefully that will help you and not confuse you if you get to a similar problem in your homework. Let's do one more problem, and I'm going to go over my 30 minutes, but I'm not going to extend this to a part 3. So here we go. Last homework style problem. So it says in the figure to the right, a circular cylinder is inscribed in a right circular cone. So see, you have a cone over here and you have a soup can cylinder sitting right in the middle. Find the lateral surface area of the cylinder if the height of the cone is 48 centimeters. They labeled that for us. The height of the cylinder is 32 centimeters. Okay, they labeled that for us as well. The height of we got that, and the radius of the base of the cone is 24 centimeters. Okay, now again, what are we trying to find? Let's highlight what we're trying to find. Find the lateral surface area of the cylinder. Okay, that's simple enough. Remember when we took that can and we took the can opener and took the top and the bottom off, and we're left with just like the tube of our soup can, and I said, why don't you cut that thing open and open it out, and we just have a rectangle? That's all we're trying to find here. Okay, so again, the lateral surface area, I'm going to put LSA for lateral surface area of a cylinder, is just equal to 2 pi r h. Okay, now the 2 pi r comes from the distance around the circle, that's the circumference of the circle, times the height. And if you fold that out, it's just a rectangle that is 2 pi r in length and h in height. So when you look at your picture over here, we need to know r. And at first look, you think, I've got it. It's 24, no, it's not. It's not 24 centimeters. The height of the cone, the radius of the cone is 24 centimeters. The radius of the cylinder, we don't know. And so what I'm going to do, and this is going to help you see how to solve this problem, is I'm going to put the radius of the cylinder right here. Okay? And it just poof, disappeared. I swear I didn't do that. Sometimes when I draw stuff, it just disappears. There it is again. Maybe it'll stay. Okay? So that's the information we need to pull this off. Now, when I did that before the first time, I recognized, hey, wait a minute. If I come from here straight down to here, notice I have a big triangle, okay, and then I have a smaller triangle. Okay, so again, the big triangle, there, that's the big triangle. And then the smaller triangle, I'm going to highlight in blue. It's going to make it look like a mess, but there, it's not even highlighting for me. There's the smaller triangle right there. Okay, now tell me about those triangles. Is there something particular that's special about these triangles? And I'm hoping you're thinking, or eventually you'll think, they are similar. Why are they similar? Could we prove that they're similar? Okay, well, first of all, this is a right angle, right? Because this altitude comes straight down by definition, and that makes a right angle out. So this is a right angle. Also, this is a right angle here. How do I know that? It really says it's a right circular cylinder. That's how I know it's a right angle. And a right circular cone. That's how I know that's a right angle right there. So we have two angles, one angle that matches. Now remember, to prove similarity, you have to do side, 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 angle, side, or angle, angle. And angle, angle seem to be the most popular out of those. And in this case, it is also the most popular. We have two right angles, and then that angle is the same on both triangles. Okay, so we're similar by angle, angle. We know these are similar triangles. Now, how is that going to help us? Well, we can compare, right? So let's draw separately our smaller triangle versus our bigger triangle. Okay, our bigger triangle has a height of 48. Our smaller triangle, do we know the height? Well, look, over here in our picture, we know our cone is 32, right? So this is the part that's not in our cone. So how about it's 48 minus 32? And 48 minus 32 is 16. So this height is 16. Okay, now again, do we know the base of the bigger triangle? Yes, that is the radius of our cone, which is 24 centimeters. Okay, what about the smaller one? That's what we're missing. And we can use proportions to find it, or a proportion. Ratios is what I'm trying to say. So we know that we could set this up that 16 in the small triangle compares to 48 in the larger triangle. X in the small triangle compares to 24 in the larger triangle, right? Then I can cross multiply, because that's how you solve for proportions. So I can say 16 times 24 is equal to 48 times X. And I'm just going to do this math real quick in my calculator. So I have 16 times 24. And then I'm going to divide that by 48 to get X by itself. So I get that X is 8. Okay, so this X right here is 8. What does that mean? That our radius over here is 8. Now you know what I can do? I can calculate the lateral surface area of the cylinder. So I have that formula right here for you. So that's going to be 2 pi R. That's what we had to do all the work to get me. R was 8. What's the height of my cylinder? That's over here at 32 inches. Okay, so that's going to be 16 times 32. Stand by. That gives me 512 pi Notice I've ignored units, but we know this is area. We're dealing with centimeters, so this is centimeters squared. Again, the lateral surface area of this cylinder is 512 pi centimeters squared. And that wraps up this section. I apologize for the long video. Usually I leave, but I was determined to get these 3 homework problems done, and they took a while. So I hope you have a wonderful day. This wraps up section 13.4. We're going to come back for 13.5 and talk about volume of these same figures, and then we're going to call 13 done. Okay, I hope you have a wonderful day, and let me know if you have any questions whatsoever.